on the development of silica media for HPLC columns. He has worked in the scientific industry for 6 years on both the analytical and preparative side. He's going to talk to us about the concentration of samples complying to US EPA 8270.
Great, thank you so much. First and foremost, thank you everybody for joining today's presentation. Like Zoe said, I'm going to be talking about the concentration of samples complying to the US EPA 8270, which is a method by the US EPA. I'm going to start off just a brief overview of what the US EPA Method 8270, what it actually entails. Most of you guys already know, but it's just a recap, pretty much the scope of application. Overview of what parallel evaporation actually is and how it applies to the environmental industry. The importance of solvent recovery in today's industry, in today's market, and some analytical results that apply to the 8270 that we actually achieved. We got these results from Phoenix Environmental Laboratories, and then we'll summarize everything up and then questions at the end. So the scope of application is for US EPA 8270. What it is, it's pretty much determining the concentration levels of SVOCs, semi-volatile organic compounds, in different matrices. These matrices can be soil, water, oil, whatever it could be. It's actually determining what these compound levels are. Here's some examples here. You see naphthalene, purine, trichlorobenzene. It's actually, the list is over 80 plus compounds, but these are just some common actual compounds for that method. So the environmental workflow, you start off with your sample preparation. So let's say your matrix is soil. You actually will start off with your soil sample, you weigh on an analytical balance of some kind, and then after that you extract the sample. Usually this extraction is done with dichloromethane because of polar chemical properties of that solvent and the fact that it's actually listed in US EPA methods. From there you have to concentrate that down. Now every laboratory is different, there's a variety of different residual volumes, most likely it's 1 ml that you're actually concentrating that down to. And that's where the parallel evaporation actually takes place. You actually do your concentration step in parallel, so you're doing multiple samples at one given time. After that, you take your residual volume and you take it to some type of analytical analysis, and that actually gives you that qualitative results of what is that concentration level inside your actual matrix. So an overview of parallel evaporation. To explain parallel evaporation, you first have to explain what is distillation. Distillation starts off with a step called evaporation. And what that is you're taking a liquid and transforming it into vapor form. That's followed by a condensation step, where you take the vapor and you transform it back into liquid form. That overall process is known as distillation. To apply the evaporation step, you need energy applied into the system. This needs to be done in some form of heat. To apply the energy out of the system, this needs to be done by some type of coolant. And now those two energies, the energy applied in, the energy applied out of the system, needs to be equal to one another so you have an efficient overall distillation process. So whenever you're performing parallel evaporation, it's always advantageous to evaporate under a vacuum source. That's because the solvent is strictly dependent on the pressure of the system. It follows the Clausius-Clapeyron equation. So pretty much what this is saying is that you're able to manipulate the solvent's boiling point by reducing the pressure of the system. So let's take dichloromethane for instance. You have a boiling point of 40 degrees Celsius. When you actually apply pressure to the system, you can actually evaporate that off at a more gentle temperature. Why is that advantageous? Well, there's many reasons. One, obviously you're going to increase throughput. Two, you're going to protect your thermosensitive samples. And then three, you don't have to worry about an upkeep cost of nitrogen. No longer using hot nitrogen to actually evaporate the solvent. You're utilizing a vacuum source. So here's the overall schematic of Vortex parallel evaporator. You have the actual platform shown here. That's what generates the heat. Remember, that's the energy applied into the system. Okay? You have your rack, in your vacuum cover here, that's where the samples are held in parallel. So you're increasing your throughput. You're doing multiple concentrations at one time. You have your vacuum source, which remember that's what's manipulating the boiling point of the solvent. You have your primary condenser, and you have a secondary condenser. Primary condenser is the energy applied out of the system. Remember, that's taking the vapors back to liquid form, and everything would be collected in the recovered solvent chamber right here. So you're able to collect the solvents that you're actually evaporating. You're not just emitting them into the atmosphere. So why is it so important to collect your solvent? Well, if you look at actual websites from the EPA, you go to the 3000 series, which is mainly the sample prep series of the US EPA, you'll see there's something called the Emissions Reduction Program. And what this is pretty much stating that you can pretty much use what any evaporation technology you would like to use. However, you have to make sure you have some type of solvent recovery system. This is verbatim, the EPA. Solvent recovery apparatus is recommended for use in evaporating concentrators. So whether you're using a centrifugal force evaporator, nitrogen blowdown technology, or vacuum vortex evaporator, it's very important to have your solvent recovery source so you can actually no longer emit solvent into the atmosphere. And this has been around for many years. There's an actual website, but you can go to, you can pretty much go to any of the methods, and they have this emissions reductions program in there. So one, the main reason you want to collect solvent is so you can suffice the EPA's recommendations. Two, what is everybody using? Everybody's using dichloromethane. Dichloromethane is a chlorinated solvent. That means it's a carcinogen. It's not fair for users to actually breathe this solvent in. It's not healthy. It's dangerous. So there's another reason. You've got to have that safe atmosphere inside your laboratory. You can see that whatever industry it is, environmental, pharmaceutical, whatever chemical, whatever it could be, everybody's approaching chemistry more green. Green chemistry is bigger than ever now. So it's very, very important to start collecting your solvent, especially as an environmental industry leaders that I see some here, that it's good to have that front line to say, yes, we're a major, you're the environmental company, and I'm sufficiently collecting this, and it shows the overall trend inside your marketplaces. So that's why this system here that I'm showing you, the vacuum vortex evaporator, which is known as the Syncor, you can see it actually has two condensers. It has a primary condenser. Again, that's the energy applied out of the system. It's condensating the vapors. It's taking the vapors back to liquid form. And also you have a post-secondary condenser after the pump. So let's say you have a user that's not too, a new user. They're not too sure about the settings, and let's say they use a wrong setting on the chiller, or they use too aggressive vacuum. That's okay. If you bypass the primary condenser by overloading with vapors, it's not the end of the world. It's still collected safely in this secondary condenser. What that means is that you're able to collect up to 95% of your solvent. Usually, it sounds like what I'm hearing in the marketplace is that most states require at least 90%, maybe more. So this is something where you can collect up to 95. The remaining 5%, you're pretty much losing if you open the vacuum cover or rinse down. It could be in the vacuum pump. Theoretically, you could probably collect up to 98 to 100, but that's just a safe guess right there. Analytical results. This is something that's important to everybody, especially you, the bigger laboratories. You have customers that demand high results. So you must be able to achieve these, whatever technology. Vacuum technology versus their old traditional KD way is something totally different. It's a totally different technology. So you have to make sure that you still can achieve the same results you were able to achieve with a KD. So we have some shown here. A lot of it is based on controlling your results, manipulating the solvent pressure, the actual vacuum setting, the rotation speed, so you can achieve high reproducible results. You can see here, the 8270, again, it's a list of about 80 plus compounds. Here's your common ones here. Naphthalene, that's usually a volatile one. You can see Phoenix Environmental was able to achieve about 90%. The lowest one was your chlorophenol, which is your more volatile compound. It's a surrogate, so that's pretty much your field goal post. You have to make sure you at least get over this one. So we're able to get to about a low 80 percentile range. So if analyte recovery is importance of the laboratory, that's fine. You use a more conservative vacuum and you're able to achieve higher analyte recovery. If not, and throughput is, you can pull a cheaper vacuum and achieve higher throughput. And this was all given by Phoenix Environmental. If you want a whole list of it, you can visit www.buki.com, analytical-results. And also, we'll have a poster presentation which has a list of all the compounds if you want to come see it. So how are you able to achieve these results? Well, one is something that's called the Flushback Module. And this is something very unique. What it is, it's a chilled zone. This chilled zone will go in between the glass vessel, on every glass vessel. And what happens is that the solvent that's evaporating up, it's going to hit this chilled zone. And what happens, it rinses back down the analyte. Analyte can adhere to the glass vessels. So when you're doing a continuous rinse down, you're going to rinse the analyte that could stick to the glass vessels back into the appendage. So that's how you're able to achieve that higher one. Plus, let's say a volatile compound of naphthalene, which is pretty volatile, it's harder to bypass a chill zone that's set at 10 degrees Celsius. So it does that continuous rinse. If you worked in an environmental lab, which most of you have, you're used to taking the vessel out, rinsing it down after the evaporation to rinse down the glass walls. This does it automatically. It's an automatic rinse down. You're using the solvent that you're evaporating, so you're not using additional solvent, and that's doing it for you. So here's a schematic of how it actually works. You can see the Flushback Module is this here. There's a coolant going inside, a coolant going out. You have your solvent level up here, and this is where you're going to capture your 1 ml or whatever your residual volume is in your laboratory. You'll capture it here. So the evaporation process starts, it hits this chilled zone, and it'll actually come back down and rinse back down to the appendage. So you think about that, yes, it increases or decreases your throughput about 5–7%, but it still eliminates that step you have to take after the concentration process of rinsing down the glass wall. So you're saving solvent because you're not using additional solvent to actually rinse the glass wall. Picture on the left actually shows a vessel without rinsing the walls with a Flushback Module and rinsing the walls with a Flushback Module. It's fluorescence in a fluorescence light, so it looks a little, that's what the red is, but you can see there's a big difference. So no matter what technology you use out there, the analyte will adhere to the walls. So it's very advantageous to have something that rinses it down. Reproducibility. The environmental industry is as competitive as ever, very productive. You need to have reproducibility. This technology, which is known as a chilled zone technology, it's no sensors, no optical sensors, because sometimes sensors they fail or something could go wrong with them, they don't go off. What it is pretty much a chilled zone. This chilled zone is actually going to keep the appendage chilled at whatever your chiller set to, again, roughly about 10 degrees Celsius. So everything in this chilled zone is going to be at 10 degrees Celsius. Everything above is going to be evaporated off. So your risk of going to dryness is very rare. Can you? Yes, but you would have to be extremely aggressive with your vacuum setting. You would have to be very harsh with it, use a very low vacuum setting to pull off. Why? Because dichloromethane, again, boiling point of 40 degrees Celsius, chemically proven that it cannot evaporate off at 10 degrees Celsius, even with reduced pressures. But there's a balance you just have to work out. Also with reproducibility, it's advantageous to have every component inside your concentration process actually communicating with one another, whether it's a pump, controller, and chiller. They all have to communicate with one another. It's important to have a controller that has a gradient program within it, so then you can actually do step-down vacuum settings. So let's say you're evaporating 80 mils of dichloromethane. You start at atmospheric pressure, which is roughly 1,000 millibars. Step 1, you would bring it down to 500 millibars. Step 2, you would bring it down to 200 millibars, and you do that entire process. At the end of the evaporation process, it self-aerates itself and goes back to atmospheric pressure. Your solvent is sitting in 10 degrees Celsius chilled zone, so if you're not there when it's over, it's not the end of the world. It's still safely stored in the 1 milliliter appendage. So just to summarize up, utilizing a vacuum source, vacuum vortex evaporator, you no longer have to worry about an upkeep cost of nitrogen. You guys can do the math yourself. Usually it's about 30 cents to $1.20 for every liter of nitrogen, depending on what laboratory and what you have worked out with your vendor. So you don't have to worry about that. Collect up to 95% of your solvent. High analyte recovery due to the Flushback Module. Reproducible results so you can keep your customers happy, and advanced automation. Again, this industry is more competitive than ever, and it's very, very important that you have automation when you're performing pretty much any of your sample preparation steps. So we can open up for questions, but I just want to say before we do, additional thanks to Greg Lawns, who is the lab manager at Phoenix Environmental, for supplying us with this data of analyte recoveries. And then also, if you need any key application notes, there's a link there. So any questions anybody could have, please ask away. Yes, sir.
How long does a normal evaporation in this take?
So let's take, the unique thing about it is you can control your results. You're not just putting it in a closed box and then letting the nitrogen blow it down. You control your results. So if you want high throughput, you just get an aggressive vacuum. Now I found that with the help of certain labs that I'm working with, I found out that there's a balance. You need to have high adequate analyte recovery so you don't worry about jeopardizing your customers' expectations by pouring too much. So let's say 40 mLs at DCM, you could do it as fast as 15 minutes. However, you're not going to achieve the analyte recovery you're used to. So it's safe to say we can do 40 milliliters of DCM in about 26 to 31 minutes and still have recoveries that are higher as any different technology out there, whether it's nitrogen blowdown or centrifugal evaporation. Yes, ma'am.
Did you do any comparisons of actual samples?
Yes, ma'am. Will we compare to different technologies, or? Yes. Yes. Yes, we're working with a very well-known company now, and it wouldn't be really fair for me to release too much without their behalf. But what we have now shown with Phoenix Environmental, they're willing to release this data. There's many other methods out there, and you know, the more you get to it, like when you're testing for PCBs, you're testing for more volatile compounds. We are finding out that there's using a certain parameter setting that you're able to achieve the same as any technology out there, but the company we're working with and ourselves aren't really willing to go forward with it yet. We're still waiting. But this here, 8270, which is your most common one out there, just pretty much the evaporation of DCM. That is, if you come see the poster presentation, you can see they're all comparable to any technology out there, or sometimes even higher in some better cases. Yes, sir. You first, please.
You said you have 2 chilling zones in this structure.
Yes, sir. So that's the